kind of entry poll for us to be able to at least understand each one of you who are attending today. So hopefully you will give some time to add, to join the entry poll so that we will understand more of you. So while you're doing that, let me go through a little bit on what we have actually shared with you previously in our webinar. So we have started earlier with control design made easy, where we have learned certain plant models and create controllers efficiently. And then we move on to plant modeling and digital twins. So it's focusing on how accurate we can do and develop system models, simulate it, and predict real-time behavior. And then next, we have explored AI-powered model-based design for smart systems. So we have seen how AI techniques can be actually integrated to enhance system intelligence and adaptability. So today, actually, we'll go through a journey where we wanted more a critical phase actually in what is test and verification, and where we will focus on verifying the design and ensuring that what we have developed our systems is actually meets our requirements and performance reliability. So this leads us to the perfect topic of what we are having today, which is verification validation of our systems. So let me take a look at okay, I guess I lost the copy of okay. Okay, anyway, let me go through again. So, so that's the recap of what we will actually going to do in this case. So I guess most of you are engineers that are working with verification and validation. So we'll go through what are the engineering challenges that, we'll begin with common challenges that we engineers face when developing embedded systems with increasing, for example, really systems that are very complex to the need for faster development cycles. So another one is we'll go through more a little bit details on verification validation techniques, where I'll show you how you can actually do your systems testing, ensuring that your models and code is actually meeting design requirements, and how to identify certain issues earlier in the design process. And then the next, we will go through actually model-based design code generation, and how we can do actually automated code generation for us to, remove a manual coding from your side as design. So, and then we'll go through a little bit of how this verification and validation ties up to the industry standards and compliance, and finally, yeah, to tie it to ensure the compliance of our systems within the model-based design workflow. So by the end of the session, I hope you will have a clear understanding of how to apply these techniques and to improve the quality of and efficiency of your embedded systems projects. So let me start with the engineering challenges. So we'll begin looking at what are we engineers are facing when developing embedded systems, because embedded systems nowadays are increasing in complexity. So we need a little bit faster design cycles in order to do this. So let me go through one challenge that we are facing actually about bugs or errors in the design. So in the start of the design, so actually this is one of one research for medical devices, where you see bug or errors in the design is usually introduced during the requirements development. So in a traditional way, through thorough code analysis is actually done almost at the end of the design cycle. Thus, most of the bugs that are introduced actually at the start of the development have already propagated to the test cycle, which means it will occur to us actually more cost or increased in development cost. In this case, so how do we make this flow better and find bugs or errors early in our design? So we will help you to actually do this using our tools for model-based design. So number one is actually requirements and artifact trainings, artifact traceability. So with model-based design, which are multi-domain models, this serve as a source of design throughput, for example, all cases of development, so that you can eliminate the barriers actually in the development stages by promoting understanding and communication across all these different teams. So I think that's the first one we wanted to share, where you work in a single environment and requirements environment. And then models are actually the center of it, the development process, and create a digital thread that enables all the systems to be required in this case. So what model-based design actually gives you is, or help you, is that the automation of the processes. So we start with requirements, specify systems behavior, and then we do simulations, right? And then from there on, we do foundation for automation, which is code generation. And then in this case, the testing is not actually only at the end of the process, of the design process, but actually it's much more within all the scopes of the system design, starting from the requirements verification, and then early design verification on your models. So we are eventually actually verifying at the start until the end of the process of the development. So in this case, we eliminate inconsistencies, manual steps, and at the same time, we cannot avoid human errors. So that, for every design engineer, we are just focusing on the algorithm development, on innovative design. So that is where I think model-based design actually gives us an initiative. So I'm just showing a little bit of examples of our customers that have used model-based design to develop their products, their algorithms, their embedded systems using a model-based approach in this case. So let me go through more details of why verification and validation is important, and how do we make use of it. So systematic use of models throughout the process, actually, where models let you try out new ideas actually in fast repeatable tests. So actually you can do many tests in a single click. So that is, I think, very important. So, and then in the case of automation, we develop most of automated coding and testing actually, and thus eliminating the manual steps. And eventually we remove the errors. So actually, this is the main objective of verification and validation, where early simulation-based verification and testing is being done through the model-based design workflow. So which succeeds in interconnecting the requirements of the product or of the project, and then the functional design, everything ties up. And then the verification of the design at the same time is tied to the requirements. So at the same time, we are verifying the design, and then we will be catching all those errors and bugs early in the design phase. So that is the objective actually of simulation-based or model-based design verification and validation. So from requirements to testing to implementation, we are able to do this verification. So in this case, in an example is a component system testing, where we want to do a simulation-based test. So in this case, MIL, which we usually say, which is model in the loop. So in this case, you are developing certain models, and then from that models, you do tests, simulation-based tests, to ensure your design meets certain requirements. So those are the things that you wanted to do for in this case. And another way is also providing you with Simulink fault analyzer, where you are able to actually place faults or errors within the system and check the behavior of your algorithms if it detects all these other faults. So this is one way, especially for safety systems, where we can see that we are able to emulate certain kinds of faults within our system and eventually be able to actually catch all of these examples of debug processes. So Simulink helps you, or model-based design helps you to actually to do this one. So another one is standards and compliance and review of static analysis. So when we're developing in or implementation models, you need to ensure that the model conforms to the industry standard. So even at the start of the design, we are already checking this requirement. So in the case, we are also linking all these systems. So you can use Simulink Design Verifier to check actually runtime errors, for example, such as division by zero or integer overflow, as well as dead logics. So we are able to actually run those systems in this case. So some requirements are impossible also to verify, maybe. So through simulation-based tests, such as safety requirements, we are able to actually do some formal verification. So there's a Simulink design verifier to prove that these requirements are always been met. So these are just examples of systems that what we can do. So let me go to a demo where we will do a requirements linking. And then we will do a little bit of Simulink test, where we can do multiple tests within a system that we wanted to do. And then I was telling earlier, right, that in just one click, maybe we can actually do a lot of testing in this case. So let me go through an example that I wanted to actually share to you guys in this case. So let me open up my model. So I hope you can see my model. So this is a position control of a DC motor. So what I wanted to share is actually how do we link requirements to the models or the design that we are going through. So an example of this one is we wanted to open, for example, requirements editor. So let's open it up and then see how we can actually use this tool. So in this case, I have already some kind of requirements that I have earlier actually imported. So if you want a new set, so actually you can just actually place a new set and then you add child or parent requirements. Or you can actually also import files from external sources. So in this case, you are actually able to share, import certain files that you want to use. For example, most of our requirements are coming from Word documents, right? Or Excel files. Or in this case, requirements document, which is RecIF, which is equivalent to requirements interface file. So maybe if you're familiar with DOORS or maybe JAMA, so I'm not sure if they are able to actually create a RecIF file or requirements interface file, then I guess you can actually export it from those third-party softwares and then actually import back to MATLAB or Simulink. So in this case, I am able to actually import it from a Word file, which I did earlier, and then provided some kind of linking in this case. So these requirements are actually already linked, some of it. So maybe I can show you. So these requirements actually can show you if they are already implemented or you want verification. So you can see here two columns in this case. So which shows you if certain requirements are already implemented or not, or if they are doing certain testing. So in this case, you can see the blue ones are the ones already implemented, for example. So let's say maybe we wanted to implement this one. So the implementation is actually seen here, where you have a link on the on the requirements editor itself, and then you can click it, and actually it goes to the model where it is actually linked. So in this case, all the design and the requirements are linked actually together. So in this case, for example, we want to link this requirement. So we just right click this one and actually link, select for linking the requirement. And then, for example, this input feedback is for this requirement. So let's say it goes here, and then, sorry, we right click this one. And if you can see, we can actually link this requirements in selection to the browser. So select for Simulink linking. So within this one, you are able to actually link your requirements on the system. So now actually you see it's now white, I mean blue. So it means it's already linked within your model. So the linking is actually very easy. It will be implemented by this, and then you can see it's being highlighted in this case. So that's how actually easy for engineers to actually have documents for requirements, and then actually link those requirements here within in a single environment, MATLAB. And then using the models that we have, we are actually linking also in this case. Later on, we wanted to link also the testing that we want to link for the requirements. So here we will see certain requirements being linked in this testing. So this is how one way of linking all those requirements. So now how do we do testing for our model-based designs? So let me close this one for the moment. And then let me open up the model back again. So here in this model, actually, we can actually open up the app that we wanted to use, which is Simulink Test. So Simulink Test, we are able to actually do multiple tests in one single click. So let me show you how we can actually do this test. So first things first is we have to actually create a harness. A harness is actually an isolation of the model that we want to test. So in this case, we want to isolate actually the controller. So this is actually the one we wanted to test. So if you see here, we are already selected the control harness for the controller, and then we can actually add another harness for this. So once we have opened the add the harness button, so actually we can specify certain inputs that we want for the model. So for example, we want it to be, is it a signal editor in this case? Is it work from workspace? Is the data coming from the workspace? So we can also do that, or a test sequence for that matter. So maybe let's select, in this case, a signal editor. And then this is actually our test component, which is the controller. And then let's say we want a scope only. So we can create those by creating a harness. So now we are able to actually create the harness within Simulink itself. So this is the created test environment. This is the input signal, which is the signal editor. And then this is the controller that we wanted to test, and the output we can actually view. So from here, actually, we can do several testing in this case. So I have prepared already a harness for you for our testing, so to be used for our simulation. So let me open up Simulink Test, and then see how we can actually easily uh, um, do multiple tests at a single time. So actually, I already have some kind of similar files that we can use actually. So we can tie up several testing. So we can create a file, and then we can create a test suite, and then we can create new test cases. So these test cases, actually, we can run multiple tests. It can be more than this, what I'm showing actually. So you can run multiple testing. You can do actually baseline requirement, baseline criteria, for example. Baseline criteria is that you want this baseline criteria data to be compared to some other simulation, and see if the system is actually responding similarly to this baseline requirement. So you can compare signals also in this case. And at the same time, you can also uh, add a requirement in this case. So you can add certain requirements for this one and then link again to your testing. So this is one way actually that we do testing and simulation within a single environment, and then easily you are able to create testing cases for your systems. So that's how we are actually doing testing for multiple types of our within our model. So to verify the functions, to verify the behavior of our systems. So yeah. So let me go back to the slides that I have. So I have shown you the requirements toolbox and how we can actually easily add requirements and link those requirements to our requirements. And then I have shown you how we can actually add a test harness for our model. And then from there on, we will add more testing scenarios for our simulation. So this is actually how we are actually doing the systems design verification and validation of our system. So now you are able to actually, so from the requirements, and then the testing, we are able to actually link everything actually together. So hopefully this helps you in your journey in your embedded design. So now let's move on to how we are actually doing model-based design, code generation. So now let's include, now we are moving a little bit on the subsystem implementation phase, where the code that will be deployed on the system is operation is being created. So specifically, this code is actually links to that point that both system requirements and documents, your models are actually together. So there are actually traceability within the model and the codes that are being generated. So later on, I will show you how this linking is being done. Actually, this one is automatically done for you from the design and to your code. So let me, yeah. So this is accomplished through the use of automatic code generation. So our core platform in MATLAB and Simulink and Stateflow all support automatic code generation to a number of different targets. So in this case, it can be CPU, which is relatively low cost or readily available. Other deployment can be GPU, a little bit more expensive to execute, but faster than CPU, right? So another way is to actually deploy using PLCs or programmable logic controllers. So often controlled like machinery or manufacturing processes in the factory, right? In the factory setting. So these are several ones. Or we wanted to deploy on FPGAs. So for applications that doesn't require really too much power or something like that. So you can actually, within these 4 levels, model-based design may be able to help you to generate these codes automatically. So you can actually, MATLAB is also able to actually generate codes on big data platforms, cloud platforms or services, or edge networks. But for this discussion is actually much more of embedded, which is much more focused on CPU deployment or maybe GPU, PLC, or FPGA. So you can automatically code generate from models you have created from MATLAB, Simulink, or Stateflow, for example, onto these targets or devices that you wanted to actually deploy. And that code generated is not only free of errors, but you can actually would have been introduced by handwritten codes, right? You can also do handwritten code, but actually these codes can be maintained within the model-based design and actually deploy it in your systems. Yeah, so this is automatic code generation for embedded systems. So let me show you a video of how this is actually done. So automatic code generation is actually generates readable, compact, fast C and C++ codes for embedded processor. So integrated codes can with handwritten or legacy, I think you can still manage to put it in and check it out using our tools also. Actually, this one, what it does is actually helps us to reduce development time because the codes are automatically actually generated for you. And then it eliminates also the errors that can be prone with manual steps in coding to refine actually executable specifications so into the target device that you wanted to deploy. And then actually you can use bidirectional linking in Simulink models to trace your model is coded or from where the Simulink model has been generated. So there's a link actually from the model that you have created to the codes that has been generated, so it can be interlinked. So in code perspective, you can look at it as the code side by side. So actually here you can see side by side, you are able to actually see the coded generated codes within this one. So automatic reusable code generation eliminates manual coding, reduces development time, and eliminates the error by hand coding. So it's the ease of actually the integration of the hand code. So let me show you a little bit of how we have done this code generation. So again, I go back to the controller that we have designed earlier. So in this case, actually, this is a reference model. So in this case, I cannot actually easily right click and then generate the code. So in this case, I have to open this as a top model. And then from here, actually, you can code generate. So we have this tool, what we call embedded coder. So in this case, helps you to auto generate these systems. So this is one embedded coder. We have other coders also that you may want to use. So for the moment, we will be focusing on embedded coder. So let me click the embedded coder. So the embedded coder have several functions. You are able also to actually do a code advisor. So this one is also checking your systems for any errors or anything that you may want these codes to be checked. So this is one way actually to do some kind of auto coding in this case. So you specify the settings of the codes in this case. So you are able to actually do that very fast. Actually, there's also a quick start button where actually you can also guide you on how to specify each of these parameters. So maybe I can open it up and then you can just see. So you can go through the process of this embedded coder where you specify the system that you want to code, the output and how to deploy it, some kind of word size. I think this one is for some kind of memory and certain optimization, and then we generate the code. So in this case, actually, we can use actually also this tab that we have done, and then see the codes that we have generated. So actually, I have earlier generated the code for you. So this is the generated code for this controller. So if you can see, it's not manual coding. So everything has been automated and then carried out. This is, I think, C++ that I have generated. So in this case, you are able to actually see also this. So certain variables are already specified depending on the requirement. So this KI, KD, for example, is actually within the model itself. So actually, these are the KI, KD parameters which are also already in the code itself. Then if you want to actually see the how to say, the traceability. If you can see, you can highlight certain parts of the code, and then you can see where it is actually coming from. So this is actually the traceability that you want for this system. So their design is actually linked also to the code that you are have generated. So you can see there are, blocks that within that controller, which is shown here, links to this um, code generated for you. So this is one way for you to see the traceability within your system. So this is way to eliminate hand coding and at the same time eliminate errors. So okay, so let me go forward for my slides. So that is what we have shown earlier, the auto code generation. So this one, we have generated the code for static code analysis, and there are a lot of tools that we can actually use for code generation, testing, and quality of your system. So another one is Polyspace. In this case, we're for testing new products. So we have this product for easier test of C++ code. So in this case, to automate and simplify also our testing work. So this is just the Polyspace tool chain that we can use for this testing. And at the same time, you will use it also with Simulink Test and requirements toolbox, where you tie everything within the model itself. So yeah, so those are the things that we do. So now actually we have shown you that the testing is not actually at the end of the project or within the test capability at almost at the end, but actually it starts from the requirements verification and now early design process. So we have done the design, and at the same time we can do actually virtual integration on the implementation of initial code generated files, where we can actually check all these reports. So these are just our easiness of things that able to help you out for model-based design, simulation, and testing. So I have done the code generation demo actually. So in this case, you are able to open up embedded coder in this case, and of that file, of that model, and then see how it works. So another way is actually we can actually how to say, test our system with PIL in this case. So maybe you want to do a testing for um, you want to implement it into a processor in this case. So let me show you how we can actually easily do a certain test of this system. So I have with me actually, I have connected a C2000 board in this case to have a check to run a PIL. So let me open up the file. Actually, this is the test file that we want. I would just like to change the configuration to a PIL mode. Let me have a moment, and then yeah, in this case, and then configuration PIL. Yeah. So actually, here you can see my hardware, my settings has been changed. So in this case, I have a board connected, TI C2000 example. So you are able to actually check certain hardware settings if you want, and change the parameters. For example, you're not limited to what I am using right now, but actually you can actually change these parameters into the packages or hardware support that that you wanted to use. So it can be any other microprocessor boards that you may want to supported microprocessor boards. So you can actually use those things. So you can specify the parameters within that test and then run the test actually within the system. So there's a PIL manager where we can actually run the system and specify the blocks that we want to have in the model. So for example, this block, the PID controller, we can actually specify as a PIL mode and then run it as is in this case to do the simulation. So I think I have a result for the simulations earlier. Let me check if it's still there. So this is actually a comparison. If you see, okay, let me open up this one. So let me compare. So there's a result that I have for simulation, if I can see here. So I have a simulation and a PIL run. So this is the run from the PIL model that I have in this case. And actually within simulation data inspector, actually you can compare these signals. So in this case is 9 and 10. So let's say, for example, we want to compare 9 and 10. So you can compare this, can see this one. So you can see two signals within the comparison and there's no difference. So what it does is actually comparing this model in the loop test and then a deployment of this controller function into the microprocessor and then compares if they have the same behavior or characteristics. So this is one way of actually not only checking the model itself, but actually the actual implementation that you wanted to be deployed. So in several cases, you may want to deploy it. In this case, in my case, is microprocessor based. So the deployment is within those requirements. So in this case, I run the comparison data and see that, you know, the results that I have are pretty much not different from each other. You can see that tolerance and difference are 0. So now I can confirm that the result of my model from a model in the loop testing is similar to the PIL testing that I have. So if I deploy it into the hardware, I am confident that it's the same. It will behave similar. So in this case, so that's how actually you can compare PIL signal. Run. So you run initially at model in the loop testing, but later on you want to actually test it as a implementation into the hardware. So this is in a microcontroller evaluation board, for example. So MATLAB supports some boards that are there. You can check it out. I think the TAs can also point out to the hardware support packages that we have for certain microprocessors. So in this case, we have an example where we wanted to run the systems in a hardware itself. So within model-based design, you are able to actually do these testings. This is called PIL processor in the loop testing. So there are in safety systems, actually there are several types. So if you are familiar with the V model or the VNV model, so actually there are several testings that starts with this one. So one is model in the loop, the one we have shown you earlier. And then you can run actually SIL or software in the loop where you code generate and then run within the processor only, internally to the system. And then later on, you want to deploy it in the hardware and see the results. So this is just some ways of you to be able to actually verify and validate your designs, right? So let me push forward. So in all of these actually requirements, um, some of the developments that can be actually tied up to industry standards or compliance. So if you're working with automotive systems, you may have heard ISO 26262 functional safety requirements. Maybe if you're working with aerospace, maybe maybe you have heard about DO-178C and other things, and maybe medical devices also you may have heard. So some of these how to say, development cycles actually require certain industry standards for compliance. So MathWorks actually supports these certification processes. So it helps you generate the artifacts, in this case, for you to develop your, I mean, test, all these things. So those are the things that you are able to do in this case. But it doesn't mean it's only for automotive, for aerospace, or medical. It's not. So actually, standard compliance, I think every product in the industry right now requires a certain level of compliance, right? So you can search of how MATLAB and MathWorks tools may be helpful for you to meet those industry standards and compliance. So let me discuss a little bit on that one, and then yeah, we can actually verify, so now we have the whole system that we have designed. So we have requirements, architecture, functions, and then we have the design, we have the models, we have the algorithms, and then we have implementation. So implementation is the CPU, GPU. If you remember, it can be PLC or FPGA. So all of these things. So we can actually develop all these systems within the model-based design. And then finally, we can integrate also the system integration part, where we have the physical hardware and then do a real time or real environment in this case. So there are a lot of tools that we can actually use to verify our implementation. For back-to-back testing, this is what I actually showed you earlier. For example, equivalence testing for SIL and PIL. So you saw that, I have compared a simulation run for a model in the loop versus a PIL run. So in this case, you are actually comparing or back-to-back equivalency testing for your algorithms. So that's one way of using it. You can use Simulink test to verify all of these requirements. Test and then tie it to your requirements. So that's the objective of this case. So yeah, so you are able to actually do simulation and back testing, and at the same time, we have shown you also earlier automatic code generation. So you could actually also generate back-to-back testings or coverage analysis for your models in this case. So you can use Simulink Design Verifier to automate and generate test vectors, for example, back-to-back testing, and to analyze certain missing coverages. So actually, if I can show you a little bit, it's not part of the demo, but I can show on the modeling, for example, if you want to see some coverage analysis. So actually, you can actually easily enable it. So within the Simulink model design, so actually you can actually enable the coverage of your system. You can enable the coverage analysis. So if you have this tool, if you have this license, you are able to actually enable the coverage of this of your testing and see how you are faring with the testing. So usually some of our tests may not be able to 100% check all the logic states, for example, or the variables that we have. So this one will be helpful for you to check those coverage of your system. So that's let me go back to my slide. So yeah, so you can actually do coverage analysis for your systems, and then yeah, this one, coverage analysis to verify completely the design, MIL, model in the loop, software in the loop, and processor in the loop for final testing. So to make all these things integrate, so if you are actually working as I said earlier, if you're working with vehicles or automotive systems. So you want to qualify your certification kits, for example, or DO certification or IEC certification. So it can be also how to say aerospace. So this reference workflow can be used, yeah, medical, automotive, and aerospace, and other safety critical workflows. So I'm not saying it's not limited to this. What I'm saying, it can be in other critical workflows that you want to actually use this system, this model-based VNV requirements. So these are just examples of our customers that have used verification and validation workflows to meet their qualification requirements. But also medical technology. So IEC 62034, you may able to use the workflow also in this case. So one of our customers also using this one for an ECG cardiogram analysis. So you see the depth and breadth of how our the systems of verification and validation and for are being tied up for especially for safety critical applications. So those are the things I think that we wanted to show. So let me just show a little bit of the model advisor where you want to actually run certain parameters, for example, the one I was talking about earlier. So how do we do a JMMAAB? I think some Japanese requirements for verification and validation. So we have what we call this model advisor. So this model advisor actually has a lot of um, how to say oops, sorry, let me go back. So there's a lot of things you can actually use for to check your compliance. So check MAB, uh, MMAB, or MISRA, or ISO 26262, or DO 178. So you can actually run this testing. So in this case, so maybe let me open up the model advisor and so that you are able to see this case. So you are able to open model advisor and then maybe you can do some checking. So usually what I do is I do it by product and select what are the compliance that you want to check for your system. So for example, you want Simulink check, for example. So these are certain modeling standards that you want to meet, for example. So you can see here DO2 checks, for example. Of course, you don't have to check everything because you may want a specific type of how to say compliance only. So you can just select those compliance checks that you want to run. So these are just certain examples of MAB, for example, JMAAB, or several models that we have. So you can actually choose what kind of simulations that you want, checking that you want to do. So error detection, for example, with Simulink Design Verifier, or other kinds of simulation that you want. So I have run an example of it. So I have results that I have. So this is just an example of the report that I have. So I run the PID SLX, the one we have actually our controller. So this is the controller that I run. And then the checks that I wanted to do. So for this case are the reports. So you can see here, you can easily actually use this artifact. So I used to work before with automotive, so you can actually use this artifact. So artifact is actually some of it are reports or certain results from testing or something like that that you can use actually for your audit, for example, in in kind of safety audits. In this case, if you're following ISO 26262 or any other compliance checking. So you are able to use actually this report to see. So I check several items where I run these things. It can give you a pass or it can give you a warning in this case. So, but warning is not an error. So it depends on how you want this requirement to be. It can also be just like a warning or a message for you. So it depends. So you can actually place which are important for you. So this already have results that are being checked for your code generation and deployment in this case. Yeah. So let me go back to my slides. Yeah. Okay. Yeah. So that's the demo for how we can actually do compliance checking with Model Advisor in this case. So Simulink check, Simulink design verifier. So you are able to actually use these tools to do your system checking. So finally, how does it ties up with the DevOps processes that you may have within your company? So usually, typically, DevOps have employed for software with continuous integration and continuous delivery or your CI/CD functions. But actually, if you have not known yet, so actually MATLAB and Simulink tools are able also to adapt to your CI/CD requirements. So you can see here some kind of stages in the system development where we have used several types of applications within MATLAB and Simulink, and how does it correlate with some of the tools that you may be already using, like for example, CI/CD for Jenkins or maybe Git or GitHub, all these requirements that you may have for the usage of ALM and continuous integration tools, cloud infrastructure. So actually, MATLAB and Simulink tools are able to actually also connect to these systems, and then you are able to do your CI/CD automations for testing. So these are the ones that I just wanted to share to you in this case. So finally, this is the agenda that we have for today. Uh, we have gone through the challenges that we have as engineers in doing verification and validation. So we have provided you some techniques that you can use for verification and validation. And then we have shown you how we can automatically code generate C++, or embedded codes. And at the same time, so we can meet. How do we meet industry standards or compliance if actually you're using safety critical workflows? So this is hopefully the agenda that will be able to help you in this case. So finally, I'm going to just reiterate hopefully what you can take away from this. So one is actually reduce manual coding effort and automation, so and verification, and then you can actually detect early errors within your system immediately after your design, and then ensure compliance with industry or safety standards, automate testing workflows with Simulink, as we have shown you, and other formal methods of testing, and then hopefully generate an efficient and real-time and deployable code in this case. So I guess for now, I will pass on to the marketing team for some final notes.